All right, so pleasure to have two rock mechanics and tunneling experts with us as our speakers, Dr. Antonio Bobet and Dr. Herbert Einstein. I will start with the introduction of Dr. Bobet, who will be first telling us about the new book on tunnel design methods, and then followed by Dr. Einstein's discussion and presentation of the tunneling in swelling ground. Dr. Bobet is the Edgar B. and Hedwig M. Olson Professor in Civil Engineering at Purdue University. He holds a bachelor's and master's degree in civil engineering from Technical University of Madrid in Spain, and a Doctor of Science degree from Massachusetts Institute of Technology. He has extensive experience in practice and areas of interest, including rock fracture mechanics, wave propagation through fractured media, and underground structures. He has authored and co-authored more than 200 technical publications, and I've had the pleasure of being one of his advisees now, I would say 12 years ago, if I'm not mistaken, 10 to 12 years ago. Dr. Herbert Einstein, our second presenter, is a professor of civil and environmental engineering at MIT, conducting research in rock mechanics, engineering geology, and underground construction, spanning a wide range of studies from field measurements to laboratory experiments to numerical and analytical models. Since 1973, his research work has resulted in over 300 authored and co-authored professional publications on the mechanical properties of soils and rocks, analysis, design, and project management of underground structures, risk analysis of landslides, and probabilistic methods in rock engineering and engineering geology. Appreciate the interest from our community and also the willingness of our speakers in joining us for today's webinar, and I would invite Dr. Bobet to start with his presentation.
Thank you, Reza, for this kind introduction. As Dr. Hedayat mentioned, I had the pleasure and the privilege of working with Dr. Einstein on a book, and you know, it was a lot of fun, a lot of work, quite a bit of time, but here it is. As Dr. Hedayat mentioned, you see the front page is the tunnel design methods. I included the QR code. Those of you who might be interested in learning a little bit more about the book, here you can have some information. And some trivia, a little bit more than 600 pages, but we are proud of having about almost 400 illustrations in tables and figures that we made the effort just to convey through these tables and figures the most important concepts. I'm sharing now the table of contents of the book. We have 7 chapters. I'll go briefly through each one of them so you have a sense of what is included in each chapter. Chapter 1 is about the principles of ground structure introduction. This is an introduction, a general description of, as the title indicates, of the interaction between the ground, the water, the support, how excavation influences that. Then we talk about characteristic curves, and you have on the top right, one of these graphs that we use to describe this method. Very important, we include concepts of the observational method, which is critical and very important in underground construction. And then we finish the chapter talking about arching phenomenon that we use then to introduce the concepts of loads into the on the support of rock tunnels and tunnels in soils. Chapter 2 is about the empirical methods and classifications for rock tunnels. We start with a general description of the methods, and then we get into how we classify these methods. And what you see here in this figure is the classification that we use. On the right-hand side, you have these classification from methods A and E. Of course, they include all the methods that we are used to. But what I think is interesting is that we use this classification based on how the rock mass is characterized, either from a qualitative or quantitative point of view. And then from that, and using the tunnel geometry, stress conditions, construction procedures, we classify those methods into what we would call maybe rock load methods, where From this information, the method come up with the load that then after a structural analysis will provide the design of the support. Direct methods where the support is given directly, or a third type of method where from all this information we get geotechnical and geomechanical properties to do the analysis. And then what we do in most of the chapters is provide some discussion and maybe our own assessment of each of the methods. And we have these sections on the most frequently used empirical methods and some discussion about each of the methods. Chapter 3 involves the direct and indirect methods for soil tunnels with effects on the surface. As with all the chapters, we start with an introduction. Then we get a little bit into the construction of these tunnels, particularly shield-based methods, because this is the method that is mostly used in soils. And then we get into how we estimate the ground deformations. So we talk about two types of methods, what we call direct methods, similar to the methods in tunnels in rock, empirical methods from some geometric and ground properties. These methods estimate directly the deformation of the ground, particularly on the surface, and then these others that we call indirect or maybe semi-analytical or semi-empirical, which is a mix of empirical with analytical and numerical methods to come up with these deformations. And we finish the chapter with how these deformations would impact structures on the surface, and we provide some information about the potential damage to buildings on the surface. Chapter 4 is about analytical methods. There are two that are similar, but there are two that we put the emphasis. One would be complex variable theory. The other one would be the relative stiffness method. Because these are analytical methods, we focus quite a bit on two-dimensional problems, but we include elasticity, we include some plasticity, and we also discuss drain and undrained loading. We spent some time looking at the limitations of these methods, particularly on how phase effects, 3D effects would be incorporated in these methods, and we list some of the approaches that could be used or people have used: the simplified method, the characteristic curve method, the alpha and beta methods, and the gap method. And then we have a discussion, as I mentioned, about how good or how not so good these methods are. Chapter 5 is about numerical methods, and you can see in the figure there is, of course, a discussion about continuum methods, discontinuum methods. We talk about the methods that we think are the one most used for tunnel design. As I mentioned, we make this classification between continuum and discontinuum, and you see the different methods that we are describing. The idea is to provide the fundamental assumptions behind each method, maybe the fundamental equations that help the reader understand what is the method based. And then we provide some examples of application of these methods. And then we finish with what we call other methods, meshless methods. We think that there are a lot of potential. And one particular application of artificial intelligence, which is artificial neural networks. So those are included in chapter 5. Chapter 6, we call it the special cases. And these are applications of tunneling to some cases that Herbert and we thought that we like, and it was our own decision to include those. So we have tunnels in seismic areas, which is a topic that very close to my interest. We also talk about pressure tunnels in rock burst areas, and then tunnels in swelling ground, which is going to be the bulk of the presentation that Professor Einstein is going to do after this very brief introduction. And then we finish with chapter 7, which is the analysis of structural components. We start again with a general introduction just to describe the different support methods, some guidelines for structural analysis, and then we go briefly covering each one of these structural components: cast in place concrete and segmental liners, steel sets. We spend quite a bit of time talking about rock reinforcement systems, particularly what we would call rock bolts, shotcrete, and then we end up briefly with composite liners and drainage in tunnels. And that provides a quick overview of the book and what the book is about. Again, the QR code for those that might be interested in. And that's the end of my presentation. I'm going to pass the thing to Professor Einstein, so we get a little more into the technical part of this presentation. Thank you.
Thanks,
Okay.
Antonio. And
Okay. See what I do here.
Slideshow, Herbert.
Okay.
perfect.
So let me put that into so I can use the mouse. Okay, so as Professor just said, I'm going to talk about this topic of tunnels in swelling ground. And in a way, this is the way one designs tunnels, period, not necessarily in swelling ground. There are quite clearly some issues which are very special in swelling ground. And but if you look at what I'm going to do with regard to how one goes from one step to the other, it's also what one does in any type of tunneling. So what I'm going to do now is quickly address the problem, the underlying processes in general, and then the underlying processes affecting tunnels. And then we go, this is literally what we do in any tunnel design, but quite clearly in this particular case, I have some other issues that are interesting in regard to swelling ground. Swelling ground in tunnels has been a problem for quite a while. These two pictures are from a book by Zia, and they are a tunnel in the Carpathian Mountains, which is now Ukraine. At that time when he wrote this, was the Hungarian-Austrian Empire. So this is about 170 years old, and this is about 20 years old. So we have this problem. This is railroad tunnels, this is highway tunnels. So what are the underlying processes? So this is in a way confusing and intentionally confusing. We have a couple processes. We talk about consolidation quite clearly. This is the opposite of swelling. Then we have swelling. This is volumetric. And then we have creep, it's volumetric and shear. And I'll show you sort of a classic settlement curve, which we do in an odometer, simply to show that these are coupled processes and combined processes. So here we have the primary consolidation, and then here we have secondary. And this is actually the interesting part, because this is not only a consolidation process where the volume gets reduced, but they're also a shearing process. So I'll show you this simply to give you a little bit of an idea on the complexity of the entire issue. I will concentrate on that, but there will be some comments on creep, because as you're going to see, this is not easily separable. Okay, so now the physical processes, physical chemical processes that we are looking at. We have clay minerals, we have sulfate rocks, and we have clay sulfate rocks. And so the clay minerals are sort of the main component in clay rocks. And so we have the classic thing that we have the particles, water is attached to the outside of the particles. And then particularly if you have expandable minerals, clay minerals, then we have this issue. And they're quite clearly much more swelling, do much more swelling than the other ones. And then see the conditions. We have the number of clay minerals, the type of clay minerals, and the interparticle distance. So this is what governs this swelling of clay minerals. So that basically a physical chemical process. Now we get into the physical chemical process of sulfate. This is rather purely chemical. So we have the anhydride here, we have the water going into it and then creating gypsum. And that, if you have finely divided, and that means sort of in the sand or silt size, then we can, if we add to anhydride of that type, sort of fine grain, add water, then we get up to 60% volume increase. If you have it in solid layers, it's much less. But the excuse me, the important point is this one here. So you need to first dissolve the anhydride, and then it precipitates out under ambient temperature. This is also quite important, something I'm not going to go into. The ambient temperature is quite important in this entire process. And then we get into the most interesting one, which is a combination of the two things, clay and sulfate. So by having the clay by itself as well, it facilitates access of water to the anhydride. And then you see this comment here. This is much more permeable, so it literally serves as a water reservoir. And then by having the clay take up water, we get an increased concentration of the anhydride dissolved in water, and then more precipitation of gypsum. And then this point here that we can have a catalyst action of the clay. So you see now the consequence. So this is clay only. So down here, this is the swell stress, and this is the clay content. And then we get the sulfate not entirely pure, otherwise this wouldn't make any sense. So we get this kind of swell stress. And then we get the highest swell stress for these guys that have the clay sulfate. So quite intensely different, whatever you have in your environment. Okay, so now we have the basic process. So we want to now apply these basic processes and look what these basic processes do in tunnels. And I'm concentrating not only because this is my home country, but because that's where we literally have lots of problems in the Jura Mountains in Switzerland, also bounding on France here and Germany. So some of the examples are actually from the other countries, but most of them are from Switzerland. This is a railroad tunnel built around 1913, 15. And this is during construction. So you have 1 meter swell during construction. This is in a clay sulfate and purely sulfate rock. Then we have also Apollina's clay, which is mostly only clay. So you see, but you see the main thing is happening here. So that's one tunnel. The other tunnel built a little bit earlier, but in the same area. And I show you this because here again we have this clay sulfate and pure sulfate, but here we have marl. So we have pure clay here and mixed with sulfate here, and you see the magnitudes are about the same. So keep that in mind. The interesting thing here is that we not only have heave of the invert, but as the invert heaves, it pushes this sidewall in. So this is not a swelling here, but the swelling here then indirectly causing this move of the tunnel sidewall into the tunnel. This is now a newer case. In the 1960s, they're actually rebuilding one of those tunnels. Again, I'm not going to go details, but the same type of rock. And what you see here is what happens during construction, a destruction of the invert. And then they needed to repair it. So this is what they had originally about 0.5 meter thickness. This is what you see here. That got destroyed, and then they redid it with much thicker and very important, I'm going to get into this later on, a smaller radius, so a higher curvature, which makes this acting as an arch. And this is something you need to look at a little bit later. This is now the recent case. This is the Friedberg tunnel about 20 years ago. Again, during construction, you see this very large heave. And then you see this is the tunnel overall. The swelling sections are here, and they're sort of enlarged, shown here. And I'll show you detail here. So we have 2 sections which we're actually going to look at quite a bit more. So the initial heave during construction was the one that I showed you, but you need to also look at this one here, that this lasted on for a year. Not as much, but really not the 0.5 meter. This is in millimeters, but still some swelling going on. So the tunnel not only has to consider the swelling during construction, but that this is not going to stop. And I'm going to show you what they're going to do about it, or have been doing about it. Okay, so this is not a classic process. Sorry, I have a cold, but I manage. So we go from testing the models to design and construction. Classic process, but quite clearly there are now some points that are related to swelling. So let's look at the swelling testing. Very simple. This is a container. Here is the sample that we put in there. We put water in, and then we get the swelling strains. And you see, this is the pure argillaceous, pure clay rock, and this is clay sulfate. So the strains are about 10 times as much here as they are here. But that's purely the swelling strain. Now we can do something. We're going to, this is very important because stresses are going to play a role both with regard to what happens as well as with regard to what we can do about it. This is simply an odometer. So the specimen is here, very classic odometer. And you see the curves here. Let me see, I have to say a little bit this thing. Okay, no, let me just go back. Sorry about that. Okay. Oh. Okay. So what we have here is, so this is the classic odometer. So we take the specimen out of the core and cut it into the small disc, and so that's quite really unloaded. And then we load it back to the original state of where it was at the very end here. And then we let it sit for a little while so it goes up a little bit. This is the swelling strain here. And then now comes the important part. Then we unload it with access to water. And as we have the access to water, we have an elastic relief and the swelling. So we have the two things together. And if you then take only the swell strain, you get this curve here. So that shows you that we have two aspects of swelling. We have the elastic relief, which we have in any material. And then we have the additional issue that we have the classic swelling with any of the mechanisms that I showed you before. Okay, so we have that. Now we have a much more sophisticated piece of equipment, which we did. This is the thesis by Delron and Aristorenas. This is a triaxial cell. And what we do a quasi-odometer in it. What that means is we load it this way, and then we have these proximity devices, which allow us to prevent the lateral extension by increasing the confining stress. So we literally do an odometer, but we know the lateral stress that we apply in order to do a quasi-odometer. So this is for undrained, and then here we have drained. We needed to do a different type of test because with the same size sample for the undrained, this would last much too long. So we do drained and undrained. Now, what tests do? We do a pure shear. So we do consolidation here. This is a classic example. Consolidate the piece of material, and then we unload. And the unloading here is on the spring line sidewall. So we have unloading here. This is the dash line, and then here the dash line here. And that can be approximated pretty well by pure shear. So we do pure shear tests. You also want to notice that here we have compression and here we have extension. So again, this is what we do, and this is what we show. So we have compression tests. So you see here, the curves are pretty much what we expected from these idealized curves that I showed you before. This is undrained, this is drained. So we get the curves that we want. I show you this, don't waste any time looking at the table. So A is essentially the compression test, and B is extension test. What I want to show you here is what we saw, the curves before, basically continue behavior. But we also have a rock mechanics behavior. So we discontinuity. So we load here and we get shearing surfaces. or we load here in the extension test, we unload here, we load here, and we get tensile fractures. So what we expect from a material that becomes discontinuous. So we have both a continuous behavior and a discontinuous behavior. So that kind of interest. Okay, so now we test, and now we need to do modeling. And since it's simply an overview, I do both volume increase and shear, but then I will then concentrate on this one. So we have the classic spring dashboard, etc. models. This is the Berger one, which is kind of complicated, but that pretty much can be used to approximate what we observe in tests. So this is very logical. Then we simply do curve fitting. So we do the tests that we showed you before, and we can basically then describe the curve with the equation. The mechanical models, this is what the Belval developed in his thesis. Again, you see this pure shear behavior. And now it's very interesting what happens. So we have this unloading in this invert here. And as we do that, we get negative excess pore pressure. And then let it sit. And then as the pore pressures increase back, then we get this curve here. So this is swelling. But now the swelling curve here is very close to the failure line. So that means very likely, and that's what was observed by Sun in China first, we then get creep in addition. So we have combined volumetric behavior and shear behavior and creep. So that's something we need to keep in mind, that very often it's not only swelling, but it's also the creep that acts. Okay. Now these are models on a lab scale. We have also, we need also to modeling on a larger scale. And I'm showing you this here again with this Kirberg panel. This is the geology there. Don't worry about this. It's kind of complicated. We're going right away to this thing here. So what we have here is GK is the German Gipskäuper. So this is the material, the clay sulfate rock. And and here it's very sulfate rich, and here it's very sulfate rich. The difference here, this has weathered and basically much more porous, and we're not worrying about that for the time being. What we worry about is this one here, which is basically below this horizontal line, it's anhydrite. Above the horizontal line, it's gypsum. So this is the natural condition. If you now look what happens before the tunnel is built, so then you see the horizontal line here, you have some groundwater flow inside the rock, not much because it's very impermeable material. But then we build the tunnel, and then we let water come in, the groundwater and also surface water come in like this. And that goes in not only in the gypsum, which is already swelled, but then it also goes into the anhydrite and then causes major swelling. But this is what happened in this section one that I showed you the picture of. Okay. So the final thing is now on design these things. And the design has got the two major objectives: prevent swelling if you can do that, or adapt the support. And so what can we do? We can affect the stress state, we can affect water excess and the chemical counteraction. This is actually what, Omar is in the audience knows about that. That's what the oil companies do a lot. They can do chemical counteraction. That's not done much in civil engineering. So I'll talk mostly of it. These two things, we can adapt the support, which I'm going to show you also. Okay. So this is prevent swelling, stress state, and water access. This is literally what I showed you here. If we go back to the original stress state and prevent water from coming in, we don't get any swelling. Quite really easier said than done. I'll show you some supports that we can try to use this, but at least we need to know the principle. If we were able to do this, then we could prevent swelling. This is a little bit coming back to what I showed you before. So we have a shape. We have this shape here, or we have this shape here, the flat invert. as we showed with many examples, there is some swelling going on. But compared to this swelling here, both here and here is minor. If you have a completely unloaded zone here, we get really major swelling. So we want to prevent major swelling by having a shape like this rather than a shape like this. Very often easier said than done, but this is at least the principle. And then we have this. Again, this is easier said than done. So we know now, if we were able to keep this situation rather than this, we would not get any swelling because we have that case that we showed. And so crowding may be a possibility, but then you talk about relatively impermeable rock. So this is, as I said, it's easier said than done. In principle, we know what to do. We need to prevent the water from coming in. But how to do this practically is not that easy. And then this is a classic thing. This is a tunnel construction, and there's something called construction water. You drill and all sorts of other things in a tunnel that creates water on the invert. And quite clearly, we want to prevent this as much as possible. So then, the least amount of water possible is desired. Okay, now we get something that Professor Bobet showed in chapter 1. This is ground structure interaction. And we have what we call these characteristic curves. They're also known as the convergence confinement method. All of you know that, but I'll quickly repeat. We have far field stresses. We have imagine the hole here. Counter stresses, no movement. And then we reduce the counter stresses, and then we get movement. So this is here. Original state, we let the counter stresses go to 0, and we get this ground characteristic curve. And then we have the support characteristic curve, the opposite. 0 stress at the beginning, and then we apply stress, and we get the elastic or elastoplastic. And then we combine these two things. So we unload the ground, we load the support, and then we get this point of equilibrium. And it can be linear or non-linear. So this is now the basis for what we can do in swelling ground. So this is now the ground characteristic curve right now when we excavate it, and then we let it swell, and then we get that curve. And we can do either this with a deformable support, so it goes up, and then at that point it starts to deform. Or we can have a rigid support, and then it looks like that. So let me now to finalize all of this, to give you a couple of examples. But this is actually what Lombardi, a very famous civil engineer in the Italian part of Switzerland. So he designed this tunnel, flat invert, and quite clearly, as I explained before, a problem with major swelling. And so he took care of this by having a deformable part here and a completely open section here. So this can swell without destroying the invert. This is again by him, even with a curved arch at the bottom of the invert, still some swelling, and he places some foam here. This is by Kirschke. This is a tunnel in Germany, again deformable support. Now this is the tunnel I showed you, the Hanstein tunnel that I showed you at the very beginning, where this was the original support here, relatively flat curvature and not quite thick, and then we replaced it by this relatively recent here. This is a rigid support, and then this is a very new tunnel where they were successful purely with a circular tunnel, having a reasonable advantage, advantageous stress state, so that all these tunnels are basically rigid. This one didn't work because it was not sufficient, but here it works in here. And then this is one that I personally was involved in the design. This is in Marl. Flat invert, as I mentioned before, not necessarily desirable, but Marl does not swell that much. So this is a molasses Marl, which is different from the Marl that I showed you before. Doesn't swell that much. So keeping this without major deformations with bolts was possible. And then we have deformable supports, again, one by Lombardi here, there's this foam out here, or we can have deformable elements here. This is not necessarily, but Professor Beer, for instance, developed similar methods. This is not necessarily only something that is in Europe. Now, this is my final point. This is remember this picture. This is the case. So we have this major deformation during construction, but I mentioned there's a centimeter swelling value also for the following years. So the tunnel has to accommodate while it is being used, the swelling, which is not huge like this, but still significant and can destroy the support. And that's what happened. So this is their original design, reasonably circular, advantageous, and then quite stiff here. That got destroyed. So this is indicated here. This is the dashed line. This is the old support. So what they did, they put in a new support here with a deformable element, and then a flat invert really in a situation like this will deform. So they put these anchors in here, and they go in from time to time to retension the anchors. So that's basically not only flexible momentarily, but flexible for a long time. So that's in a way quite weak and controllable. So classic observation. Okay, so I come to the end. This plants can be seriously damaged. We saw that. And that the definitions here, I'm not going to repeat that, but then this process that we do for any tunnel, we can do special experiments for swelling rock. We have models that we can use to assess the behavior of swelling rock, and then we can do something about it to a limited extent, that you see. Shapes, water access, and the ground structure. Okay, that's it.
Thanks, Dr. Einstein, for the presentation. Very interesting topic. So at this point, I invite the attendees to please either unmute themselves for questions or use the Q&A option for raising questions. And I'm not sure if I see any question yet, but this is now the time for questions. I guess while folks are finding where to post questions, I can start by asking mine. Would be curious if you would suggest, Dr. Einstein, any type of pre-excavation grouting, specifically for cases where the swelling can be predictable.
Well, in principle, yes. The question is what kind of grout can you use to get into the slow permeability grout? But that's an issue. It has to be a low viscosity.
Yeah, I was thinking like mainly a type where the primary interest would be to provide a barrier for the water infiltration into the problematic areas.
Yeah.
Yeah, and how about the case? I mean, obviously, we commonly have in a mechanized tunneling the practice where we over excavate the ground, and we have usually the annulus space that eventually will get filled by the two component grouts. Would there be some practices that intentionally the over excavation can be larger than usual to accommodate for the potential swelling?
Yeah, definitely. Yeah. That's basically what they do with these. I only show the designs for the permanent accommodation of swelling, but quite clearly that's a good idea. But yeah, it's case dependent. But in principle, I would agree with the suggestion that that's actually a good idea.
Okay, perfect. Let's see if there are any questions posted. Yes, I do see one here. So let me go ahead and read. We have a question from Estekatsikis. Apologies if I mispronounced. Very good presentation. I would like to ask what your preference would be, flexible lining or rigid, not only for swelling, but also for a squeezing condition.
For what condition?
A squeezing condition. A squeezing ground condition.
I don't know. So if you've seen these cases, let me back up. If the deformation magnitudes are small, and based on that case that I showed you last, where we talk about centimeters per year, it has to be smaller than that. Then you can use a rigid line. If it's in the magnitude, just simply by looking at this case, I'm not saying I can generalize that. But if you look at that case where you have centimeter per year, it's quite obvious that only a liner that can accommodate the deformations can be used. Or you have to be prepared to go in after 10 or 20 years and repair the tunnel. That's another option. So you can put a rigid liner in, it gets destroyed, and then you go back in. And that's actually what happens right now, not the tunnel I showed you last, but one of the tunnels, the Belgian tunnel in Switzerland. They have two tunnels parallel to each other, each with two lanes, and they're basically destroyed. So they're building now a third tunnel, because this is the major north-south route in Switzerland. They cannot take one of the tunnels out of commission while they repair it. So they're building a third tunnel and then repair the other two while they have the third one in operation. So that's another option. So that was a rigid liner got destroyed.
Okay, thank you. Now we have a number of questions, so let me go through the order. Peyton says, thank you for the presentation. What causes the dramatic change in water flow paths from before excavation to after excavation?
Well, we basically have a permanent opening so that the gradient is completely different.
Right. Masood asks, following up on the question I raised earlier, have you seen any examples of pre-excavation grouting to form a water barrier? Have you seen any field test rejecting the success of pre-excavation grouting?
I don't know. Not in this area. I have Norwegian friends who, and that's mostly in their process of drill and blast. They're adamant about pre-excavation grouting. So that's basically the practice in Norway, but that's not in Sweden. They basically do pre-excavation grouting, and they're adamant about it.
Next question from Sator. Thanks for the great presentation. I wonder if there is any chemical for injection in swelling ground to prevent the process of swelling.
But there is, but I don't know anything specific about it. But as I said, the oil industry is doing this a lot, and I'm sitting up to be able not to say something.
Okay. So, Abdul Hakim asks, thanks for the nice presentation. Is there any relationship between clay soil plasticity index with the swelling potential?
Yeah. Look at Lamb and Whitney. I don't have this in my head, but Lamb have a relationship.
Okay. Carlos, thanks both of you for the presentation and the book, and also thanks me. So thank you for the comments there, Carlos. I read with the expectation of a question, but I appreciate your comment there. Jack asks or says, thank you for the book question. Laboratory tests were discussed, but what about larger scale geophysical or mechanical borehole or exploratory audit tests? Also, mentions that Q&A function is turned off, but I encourage folks to use the chat option, and apologies for that. So reiterating the question about the potentials for larger scale geophysical and mechanical borehole or exploratory audit tests.
Well, I've not done anything of in principle it should be possible, but I don't know.
Right. Well, I can see potentials where if we know, and have the opportunity to predict well the swelling ground condition, that we might have some scaled version of the tunnel with some, I mean, as long as we follow scaling laws, that we would have a better understanding of the deformation to then help with the design of the support. But I don't know how feasible it would be to have that prediction and the time and investment to do the physical modeling.
Well, a scaled physical model, I don't know. I'm somewhat skeptical if that's doable. But there's never any harm done that the running tests be then whatever scale that is. But again, I have to admit that I don't like.
Okay, perfect. And I think I had a chance to go through the questions, but folks, feel free to still use that time and QA option if you have any additional questions. I think Jack is following up. One example of borehole test would be measuring the in situ stress.
What? Can you repeat that?
Yes, one example of borehole test would be measuring the in situ stress.
Yeah, that quite really would be the primary condition that we relieve the stress from. So knowing the in situ stress quite really is something quite important. And measuring this with whatever borehole tests and all, that's certainly something that would be a good idea. Yeah, and actually, since you bring this up, the interesting thing in the Ural Mountains is that the one of the horizontal stresses is greater than the vertical stress, because the Alps push the Ural Mountains until you have sort of a southeast, northwest horizontal stress that's greater than the vertical stress. So knowing the stress state is quite important. That's a good thing.
Okay, perfect. Masoud is following up. What is the range of confinement needed to suppress swelling in clays?
Well, that depends. This is literally my little example with the odometer. So you want to go back to the original stress state. So whatever that is in that particular location. Maybe an additional comment. If you have a rigid support and the swelling occurs against it, then you will build up your stress acting on the swelling ground. So you need to model that too if you want to take that in consideration.
Okay, yeah. Okay, Juliana is asking, is climate change affecting the rate of deformation in swelling ground?
I don't think so.
All right. Okay, so we have another question here. Is that if the tunnel is made watertight with all around membrane, would it reduce the swelling potential?
Only with regard to water that comes from inside the tunnel. The main thing is that the water that causes most of the swelling comes from the ground itself. So that's where you raise up that comment about over-excavation and pre-driving and so on. That's the way to go. I don't think a membrane will help a lot with regard to swelling, because the membrane is preventing water from inside the tunnel going out, and then in the final operation quite really the other way around. But then the membrane itself does not do anything to reduce swelling.
All right, Masoud is following up on asking, does applying axial confinement affect the swelling strain in lateral direction?
If you confine it, yeah. That's the odometer. So you put a vertical stress or axial stress on it, and the odometer does not allow you to expand laterally. And that increases the lateral stress, and in that special triaxial cell, we can measure that. But in an odometer, usually, unless there's special odometers which allow you to do that, you don't know what the lateral stress is. So you need to know the three-dimensional stress, because it's not only a one or two-dimensional mechanism.
Mhm. Right. Another question that came to my mind, I mean, for such a susceptible or sensitive type of rock that would be influenced easily with the water and swelling, what are your thoughts about maybe considerations that have to be in place with just the process of the drilling and the extraction? I mean, obviously we commonly use water as the fluid medium for drilling. Would that affect it, or are there any alternatives to water-based drilling techniques?
Well, I answered this indirectly, because much of the stuff, by the way, on the swelling is admittedly quite old. But one of the issues we have is what we're addressing is that if we drill our probes that we then use to test in the lab, and we do this drilling with water, then that changes the boundary conditions, and that's not a good idea. So many of those samples we used were drilled with oil, not with water.
Wow.
And then also in the lab, any cutting, coring, and so on was not done with water, because exactly that issue that we changed the basic conditions, and then it's not correct.
Okay, very interesting. All right, Masood has another follow-up. Would excavating a trench at the invert help releasing the swelling pressure or suppress the heave?
Again, only in the way, if you look sort of a flow net around the tunnel in your mind, and then if that trench removes some water from swelling zones, it might. The trench is, however, quite necessary for what I show you this picture, where during construction you have flooding of the invert. You can reduce the flooding of the invert by having a trench where you concentrate your water. That's basically done standard in most tunnels. Not in the one I showed you, but most tunnels have a trench to remove the construction and water coming from there.
Right, very good. Let's see. Juliana and Assad say thank you for the presentation. So appreciate your attendance as well. And I would like to thank the presenters one more time. Really appreciate the time that they spent, and I really appreciate the opportunity. I'm thinking that I've never had a chance where I would hear from the authors of books that are provided in our field. So I think this is a great opportunity that we have had. And speaking of the time-dependent behavior of tunnels, our next webinar, which is scheduled in 3 weeks, is going to continue with this trend. And we will have the topic entitled as Lessons from Alpine-based tunnel excavation on squeezing ground and pre-excavation grouting, that will be offered by our colleagues from Emplenia in Austria. So looking forward to having that webinar in 3 weeks. Same time, please mark your calendar 3 weeks from now, and stay tuned for some of the announcements through our LinkedIn as well as ARMA community. And appreciate everyone for the attention and attendance, and have a great day.
Thank you.
Thank you. Thank you, Reza. Bye.